Section 4.2, Basic Concepts of Probability. What is the probability that I will win the raffle? What is the probability that we will have a boy? What are the odds of losing the game? We ask questions like this every day. In this section, we'll look at how probabilities and odds are calculated and how they are different, along with some properties associated with probabilities. Now, before we get started with how to calculate them, let's make sure we understand some of the terminology that's used when discussing probabilities. An event is the outcome of an experiment. An event can also be thought of as a subset of this sample space. An experiment is a process where outcomes are obtained. Now, those seem a little bit similar, so let's make sure we understand the difference. The experiment is the process. I like to think of it as the action. So tossing a coin, choosing a card from a standard deck, things like that is the action that happens. The outcome is what we observe. So getting a head on that coin or drawing a queen of spades as our card. So the experiment is the action or the process, where the event is the actual outcome that happens. The sample space is the set of all possible outcomes of an experiment, and it's usually denoted by the letter S. So this is everything that could happen. So there are 52 different cards in the deck, from hearts and spades and face cards and all different things. Those are all the possibilities. I might be interested in something very specific, but that's what's possible. A simple event is an event that cannot be broken down. A simple event is pretty much what it is. It's not made up of smaller little events. And I think the contrast between a simple event and a compound event will be more obvious as we work through some examples. So let's take a look at example 1. Start with something we're usually familiar with. Toss a fair die and observe the number appearing on the upper face. Describe the sample space. Describe a simple event. Describe an event. So describe an event that's not sample. So a fair die has the numbers 1 through 6, or they might have the dots representing 1 through 6. So our sample space S is, and we do want to use braces to define a set, 1, 2, 3, 4, 5, 6. So remember, the sample space is everything that could happen. Now, what could be an event? And there are lots of events. An event might be something like, let E be the event. We get a 2. That's an event. It's possible because it comes from the sample space. Now, an event that's not simple might be something like this. Let F be the event. We get an odd number. Well, what does that event include? That could be 1 or 3 or 5. Now, 1, 3, and 5 are the simple events, but when I put them together and say the event is getting an odd number, then that's a compounded event. So just the individual outcomes in a sample are usually the simple event, but when you put things or group them together, then that's a compound event. Okay, example 2. Toss a fair coin and observe the side of the coin that faces up. Describe the sample space. Describe a simple event. So the sample space, there's only 2 possible outcomes. Again, I'm going to define my set with braces. It could either come up tails, so we'll use a T for that, or heads. That's the only possibilities. A simple event here might be let E be the event. We get heads. That's one of the choices from our sample space. That's pretty much it. If the coin is tossed twice, discuss how the sample space changes. Describe a non-simple event. Okay, so with just one coin, I can either get heads or tails. That's my entire sample space. But if I toss it twice, now I have a new sample space. So I could either get heads both times, or I could get tails both times. So the first T represents the tails on the first toss, the second T represents tails on the second toss. I could get heads the first time and tails the second time, or I could get tails the first time and heads the first time. So now our sample space is a little bit larger. In our previous, when we just tossed it once, our sample space had two elements or two items, tails and heads. But when I toss it twice, now my sample space has increased to 4. Heads, heads, tails, tails, heads, tails, or tails, head. And a non-simple event here might be something like, let E be the event that we get a head first. Okay, well, that might include more than one event. So if I look at my sample space, that includes heads, heads. Now I didn't specify what would happen on the second toss, just the first. That could also be heads, tails. So that's the difference between the sample space and an event. An event, we're wanting something specific to happen. Okay. When we say probability, we are referring to a numerical measure between 0 and 1 that tells the likelihood that an event will occur. So no matter what, all your probabilities have to be between 0 and 1. They can't be less than 0, meaning they cannot be negative, and they cannot be larger than 1. An event with probability of 0 cannot occur. Completely impossible, at least in the sample space that you're referring to. Whereas an event with a probability of 1 is certain to occur. Probabilities closer to 0, if they're not exactly 0, but maybe they're close, are much less likely to occur. But probabilities closer to 1 are more likely to occur. So they're not guaranteed to happen, but they're more likely to occur. So something, just to give you an idea, something with the probability of 0, let's say with rolling our die, the probability that I get a number larger than 7. Well, that's impossible because the largest number you can get is a 6, so that'd be a probability of 0. But if I said, what's the probability of getting a number smaller than 7? Well, that's 1, because anything I get on the die is going to be smaller than 7. So that's a certain event versus an impossible event within the sample space. Okay, next we want to make sure we are comfortable with notation. As you've seen me do so far, events are denoted by capital letters such as A, B, or E. Sometimes we like to use letters that are relevant to the context of the problem, which is okay. Probabilities are denoted by P parentheses A, or we read that P of A, similar to function notation like f of x. We also have two types of probabilities, empirical probabilities and theoretical probabilities. Now your book uses some different notation, but I chose to use empirical and theoretical because they're more standard across probability and statistics. So just keep that in mind. You might not see these identical terms in your book, but they're more likely to appear in your homework on ALEKS. Okay, so what's the difference? Empirical probabilities, this is when we compute probabilities based on events that have already occurred. So it's something that's actually already happened. And the way you set that up, the probability of E is the ratio or fraction where the numerator is the number of times the event E occurred or occurs over the total number of events that have occurred in general. So we're taking that subset of something we're interested in and comparing it to all the events that occurred. Theoretical probabilities, on the other hand, is when we compute probabilities based on what we think will happen. So it hasn't happened in reality yet, but just based on what we think will happen. Usually, we're going to assume that all outcomes of the sample space are equally likely. There's some times where that's not applicable, and you want to be careful with that, but usually we can assume that the outcomes are equally likely. Like in the case of a coin, we assume that we have just as much a chance of getting a tail as a heads. And the same thing with a die. We figure we have just as much chance of getting a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so here very similar. The probability of E is the total number of outcomes of E, the event we're interested in, over the total number of outcomes in S, the total sample space. So the wording is a little bit different, but mostly we're finding the same thing, whether it's an empirical probability or a theoretical probability. Let's take a look at example 3. In a random sample of 400 students from local high schools, it was determined that 325 have plans to attend college. Determine if this is a theoretical or empirical probability, and then find the probability that a randomly chosen student from a local high school will attend college. Okay, so is this theoretical or empirical? Well, it looks like we've already talked to these high school students and we know what's going on, so this is an empirical probability. It's something that's already happened in the past. Now, we don't know what's going to happen with this randomly selected student, but we're going to base our probability on what has already happened, that out of 400 students, 325 plan to go to college. So we'll say the probability of going to college. Actually, let's identify or give this a name, a letter name. So we're going to let C equal plans to go to college. So the probability of C equals, well, how many already actually do plan to go to college? 325, that goes on top. And the total number of students that we talked to, 400. Let's see what we get here. So that's 0.8125. Be sure to pay attention to the directions in your homework and what is asked for the rounding. So if this were to be rounded to 2 decimal places, we would say 0.81. Other times you're asked to leave your answer as an exact fraction, especially if the decimal's not nice like this. You can use your calculator to do that if you press math and then that first selection arrow FRAC math frac, that'll turn your answer into a reduced fraction. So 0.8125 is what we got from our calculator, rounded to 2 places after the decimal, 0.81 or 13/16. Example 4. 400 tickets were sold for a raffle where the winning prize was tickets to a popular concert. One person bought 15 tickets. Determine if this is a theoretical or empirical probability. What is the probability that this person will win? Now, although the event has happened that the tickets were sold, that's not what we're interested in. What we're interested in is whether we win or not, or whether this person wins or not. And since that hasn't happened yet, we're going to assume that this is a theoretical probability. We're going to try to predict what happens based on theory. As we mentioned before, we're going to assume that each ticket has an equal chance of winning, meaning there's not some bonus ticket or anything to skew our results. So if one person bought 15 tickets, or let's define this, we'll say let T equal having a winning ticket. no, let's say this. Sorry. Ticket is a winner. So the probability of T is, well, for this guy, he bought 15 of them, but there were 400 altogether. So that's 0.0375. Round it to 2 decimal places would be 0.04 because of that 7. Or if we wanted it as a fraction, that'd be 3/80. When trying to calculate a probability, we may not always be told the total number of outcomes. So in both examples, we were told there were 400 students or there were 400 tickets. They might not be stated that explicitly. So we want to be careful when trying to determine how many possible outcomes are actually in the sample space. Let's take a look at example 5. A couple plans to have 3 children. Assuming that having a boy is equally likely as having a girl, list the sample space. Determine the following probabilities. Okay, so there's quite a few ways that this can happen. And we'll just start listing them out. So, of course, we could have boy, 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 all boys, or girl, 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 or some combinations thereof. So maybe boy, boy, girl, and boy, girl, 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 boy, and girl, boy, 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 girl, boy, and girl, boy, girl. So there are 8 possibilities. There's 8 events in our sample space. Okay, so we're asked to find the probability of the following events. Event A, the first child is a girl. Let me back up here. There are 8 elements in our sample space, and each one is equally likely. So we say the probability of an individual event is 1/8. Now I'm being asked to find the probability that the first child is a girl. What I want to do is go through my sample space and take into consideration every outcome where the first child is a girl. It doesn't matter what happens in the second and third child, but just that first one. So it looks like we have that happens with girl, 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 and girl, girl, boy, and girl, boy, girl. And if each one is an 1/8, we add those together for 3/8. So there's 3 ways that that could happen. Event B, there are more boys than girls. So for the probability of B, we're looking for all the times that we have 2 boys versus 1 girl. Or we could have 3 boys. That could be a possibility also. So this could be when we have all boys, because that's 3 boys and 0 girls. Or boy, boy, girl would work. Or girl, boy, boy. Or boy, girl, boy. So how many ways is that out of 8? So we know there's 8 possibilities, but altogether that's 4. And make sure to reduce all your fractions, or 1/2. Back up here, probably a better way to do this, even though we did 1/8 plus 1/8 plus 1/8. I'm kind of getting ahead of myself. If we were to just go through and count the number of ways that that happens, so each event 3/8, we would have gotten the same thing. Okay, example 6. In a survey about political party affiliation, 567 residents identified as Republicans, 493 identified as Democrats, and 321 identified as independent or other. What is the probability that a randomly selected voter is Democrat? So first I'm going to let D equal a voter is a Democrat. Okay, this time I don't know how many total voters there are. I know how many are Republicans, how many are Democrats, and how many are independent or other, but I don't know a total, so it's up to me to find that. The best thing we can do is to add up what we have, assuming no one is affiliated with more than one. So we have 567 plus 493 plus 321. So that's 1,381. So we can think of that as the total number of possible outcomes. So to find the probability that a randomly selected voter is a Democrat, out of 1,381, we know that 567 are, 493 are Democrats. Let's see what we get. 493 divided by 1381. So in my calculator I get 3.3569. I have quite a few places after that. But probably I'm going to round this to 2 places after the decimal. So that would be 0.36. Okay, example 7. A fair die is rolled twice, and the sum is calculated for the numbers that appear on each die. List the sample space and determine the following probabilities. Okay, so if I roll 2 die, well, I could get 1 on the first die and 1 on the second die. I could get 1 on the second die and 2 on the second die. And if you can kind of figure out the pattern here, this sample space is kind of big, so you don't have to write down every single value if you don't want to, but this goes all the way down to 1/6. Well, then it could be 2 on the first die and 1 on the second, 2 on the second die and 2 on the second, all the way down to 6. And then it could be 6 on the first die, 1 on the second, 6 on the first die, 2 on the second, all the way down to 6, 6. I'll leave it up to you if you need to fill that in completely, but that's pretty much what's going on with this type of sample space. And I'll tell you that there are, if you think of 6 in this row and 6 going down, 6 times 6, there are 36 elements or things that could happen in the sample space. Okay, so for part A, the event E, the sum is greater than 10. Well, if we're going to be greater than 10, that means we get a sum of 11 or 12. Well, let's list out the ways that that can happen. For 11, that could be 5 and 6, or 6 and 5. We could also get and that's it. That's it for 11. And for 12, the only way to get 12 is to roll a 6 and a 6. So this is, what do we call this? This is event E. So now to find the probability of the event E, well, the number of ways that I can get an 11 or a 12, because that's a number that's bigger than 10. I'm not including 10 because it said strictly greater than. Well, there's 3 ways that that could happen. And the total number of elements in the sample space, 36. So that reduces to 1/12. And in a problem like this, they would probably ask you to leave it as a reduced decimal or reduced fraction. But if we want it to go down to a decimal, that'd be 0.083, where the 3 is repeating. So to 2 decimal places, that would be 0.083. 0.08. We're also asked the event if the sum is not even. Okay, well, if it's not even, that means the sum is odd. If the sum is odd, that means it could be 3, 5, 7, 9, 11, and that's it. So what we need to do is list all the ways to get a 3, a 5, a 7, a 9, or an 11. And that one is actually going to take a lot longer than I anticipated, but here's kind of a shortcut. The only possible sums you can get on the roll of 2 die is 2 through 12. And there's kind of a pattern here, and this is just in the interest of time. There's only one way to get a 2, to roll a 1 and a 1. There's 2 ways to get a 3, 3 ways to get a 4, 4 ways to get a 5, 5 ways to get a 6, and 6 ways to get a 7. And then it starts to go back down. There's 5 ways to get an 8, 4 ways to get a 9, 3 ways to get a 10, 2 ways to get an 11. We just saw that with 5 and 6 and 6 and 5. And only 1 way to get a 12. So if we add up, and these are not fractions, if we add up the sums being odd, so let me label this sums, that means we're going to take 3, 5, 7, 9, and 11. So that's 2 plus 4 plus 6 plus 4 plus 2 over the total number of outcomes, 36. That's 18 over 36, which is 1/2. Which kind of makes sense because either your sum is going to be even or odd. One thing you want to pay attention to, and this will be helpful later on, the sum of all the probabilities of the simple events, so not compound events like the sum being odd, but the simple events, one getting a sum of 2, 3, 4, 5, have to sum up to 1. However a sample space is broken down, whether it's tails and heads, or the roll of a die, whatever's going on, all the simple events have to sum to 1. Okay, complementary events. Sometimes we may need to determine the probability that an event does not occur. This is when the complement of an event is used. So the complement of an event A, denoted by A bar, so that little bar on the top, is the event that A does not occur. And we just mentioned that all the events in the sample space have to sum to 1. Well, for any situation, either that event does or does not happen. So here for number 1, the probability of A plus the probability of not A, that's another way you'll hear this notation read, has to equal 1, because either it does or it does not. Either I do or I don't roll a tail. Either I do or don't pick the right card out of a deck. So those two complements have to add up to 1. And if we rearrange that equation a little bit, the probability of A bar or not A is equal to 1 minus the probability of A. And just to mention, if you come across other notations for complement, you'll also see A prime, kind of an apostrophe that also means not, or a C with an exponent of a C, or subscript rather, superscript of a C for complement. So I just want to mention it to you, just in case you saw it in another textbook or on a website, it means the same thing. Okay, example 8. A veterinarian tells you that if you breed 2 cream-colored guinea pigs, the probability that an offspring will be pure white is 0.25 or a quarter. What is the probability that an offspring will not be pure white? So let A be the event that the offspring is white. And we're already told that the probability of A is 0.25. So if I want to find the probability that it's not white, that would be 1 minus 0.025 or 0.75 or 3/4. Refer back to the sample space for rolling a fair die twice. Find the probability that the sum of the die is not 4. Now here's where a complement really comes in handy. If the sum of the die is not 4, that means it could be 2 or 3 or 5 or 6 or 7 or 8 or 9, 10, 11, or 12. Now we could go and add all of those up, but another way to do it that would save us a little bit of time is to use the complement. So I'm going to let F be the event that the sum of 2 dice is 4. What's the probability of F? Well, let's list out the sample space. Let's do that. So F, the way that can occur is a 1 and a 3, a 2 and a 2, or a 3 and a 1. And you can verify that back with what we wrote down. So this is 3 ways that this can happen. So the probability of F is 3 over 36, or that reduces to 1/12. So if I want to find the probability that it's not a sum of 4, everything else, all I have to do is say 1 minus 1/12. Which if you find a common denominator, I'm changing that 1 into 12 over 12 would be 11/12. So I didn't have to go back and do all that work of adding up all the other cases. It was just easy to take the event that I had in front of me and find its complement and subtract that from 1. Okay, last thing. Oftentimes we hear the words probability and odds used interchangeably. What's the odds of that? What's the probability of that? And truly they're not the same. While we've learned that probabilities are the ratio between a specific event A and all possible outcomes in a sample space, odds compares the event A and its complement A, not A. So even though we, in regular everyday language, we think of them the same, they're not quite the same. A probability is usually going to be a percentage or a decimal, whereas odds is a ratio of comparing the event happening versus it not happening. So here's a little table, a formula for odds. And we also have odds against and odds for. So if I want to calculate odds against an event A happening, it's the probability against A, or you can think of that as A not or not A, and the probability for A or the probability of A. So that's probability of not A over probability of A. But if it's the odds for an event happening, it's just the reverse. The probability of A is on top and the probability of not A is on the bottom. You'll also see odds expressed as a ratio A colon B, where A is the number from the numerator and B is the number from the denominator. Let's take a look at one example as we wrap up. In an urn, there are 5 red marbles, 3 green marbles, and 2 blue marbles. 1 marble is selected at random. What is the probability that the marble is not blue? Okay, so let's stop right there. I'm going to let B be the event. The marble is blue. And we know how to set up a probability. Well, first I need to know how many marbles there are total, because they didn't tell us explicitly. But we can find out by adding up what we have. So 5 red marbles plus 3 green marbles and 2 blue marbles gives us a total of 10 marbles altogether. and I'm interested in the event that I get a blue one. Well, there's three possible ways to get, or no, there's two rather, two ways to get a blue marble, so that goes on top, and that reduces to 1/5. We're going to leave that as 1/5. Now the second question is, what are the odds against, so that part matters whether we're saying for or against, the odds against the marble being blue. From our formula up above, we know we need another calculation. We need to know the probability of not getting a blue. Well, again, rather than adding up all the greens and the reds, I could do that, and there's nothing wrong with that. To find the probability of not getting a blue one, I can just subtract the probability of getting a blue one from the number 1. So again, I'm going to use a common denominator and change my 1 into 5/5. So that is 4/5. And since we're going to do odds next, let's leave those as fractions. So now if I want odds against, remember this time I'm comparing probabilities, I want the probability of not being blue to be on top and the probability of blue on the bottom. Well, not blue is 4/5, that goes on top, and getting one that is blue goes on the bottom. Now when you have a fraction within the fraction and the denominators are exactly the same, you can cancel them, and we end up with 4/1. Now usually we would go ahead and just say 4, but remember odds is really comparing two things. So I would say the odds against getting a blue marble, I can write that as 4/1. So I'm more likely to get something of another color than to get a blue marble. And if I wanted to do odds 4, I would just flip that whole ratio and it would be 1/4. So I hope you realize the difference between odds versus probabilities, because they're very easy to mix up. Maybe next time when you hear that, you'll know the difference.